In this video, we'll talk about the ratio and root test. I did talk about ratio and root test in a previous video, but this video is more aligned with your textbook, um, so it's more up to date. But let's see what's the difference between those two videos, because there is no huge difference. So if you understand one way, you'll understand the other way as well. So let's just take a look at the ratio test. So the ratio test. In this video, with the current edition of the book that we have, it says let sum as a sub k be an infinite series and let R be limit as k is approaching infinity of absolute value of a sub k plus 1 over a sub k, and if R is between 0 and 1, the series converges absolutely, therefore it converges. If R is greater than 0, it diverges, and if R equals 0, the test is inconclusive. So again, pause this, read it again, and let's go and look at the previous video that I made to see what's the difference between these two. So if we take a look at the video that we discussed initially, look at the ratio test. It says let sum as a sub k be an infinite series with positive terms, and let R equal limit as k is approaching infinity of a sub k plus 1 over a sub k, and then we have the same conclusions. R between 0 and 1 it's makes the series converges, R greater than 1 the series diverges, and R equals 1 test inconclusive. So the difference between these two is in here we have positive terms, so then we don't have any absolute value signs, while in here we have any type of series, so not necessarily positive, but we put absolute value so that we don't worry about alternating signs. So I hope it makes sense. Now let's go further. For example, show that the series sum as k goes from 1 to infinity of k to the k over k factorial converges or diverges. So looking at the ratio test, we're going to calculate the limit as k is approaching infinity of, and maybe we should say this term, it's our a sub k, so it's k to the k over k factorial. So our a sub k plus 1 term is going to be k plus 1 to k plus 1 over k plus 1 factorial. So going back to the problem, we have the a sub k term, which is this one here, divided by the a sub k. So how do we divide? We multiply by the reciprocal, but we also did a little bit of algebra by saying k plus 1 to k plus 1 is k plus 1 to k times k plus 1. We use properties of exponents. And k plus 1 factorial is k factorial times k plus 1. So then we can notice how this term cancels this factor with this factor, and this one with this one, and we have a limit of a polynomial, if you want, at the numerator it's k exponent and the denominator k. So we have this term here, which is the limit as k goes to infinity of k plus 1 over k to the k, and that is equal to e, which is greater than 1, so the series diverges. So let's take a look at another example. It says use ratio test for sum as k equals 1 to infinity of 2 to the k over k to 99. And if I remember well, we actually did this problem, so I'm not going to do this problem again. I'm going to do a different one. So let's say instead of doing this problem, let's do sum as k goes from 1 to infinity of negative 7 to the k over k squared. So again, using ratio test, a sub k is negative 7 to the k over k squared, while a sub k plus 1 is negative 7 to k plus 1 over k plus 1 squared. So limit, or R equals limit as k is approaching infinity of a sub k plus 1 over a sub k in absolute value So equals limit as k is approaching infinity. If we put absolute value, we don't worry if the terms are positive or not. They will be positive. Absolute value of negative 7 to the k times negative 7. I just write that instead of k plus 1 at the exponent over k plus 1 to the second times, and now the reciprocal, k squared over negative 7 to the k. So this cancels with this one, and we end up with negative 7 k squared and k plus 1 to the second. So the degree of the numerator is the same with the degree of the denominator, so the answer will be absolute value of negative 7, which is 7. This is greater than 1, so the series diverges. There is another example here, show whether the series 10 to the k over k factorial converges or diverges. Again, it's an example similar with what we've done. And I think we went over that. Let's take a look at another problem. So in this case, a sub k is negative 1 to the k. Okay. So I wrote a sub k and a sub k plus 1 because I had a few issues. So now r equals limit as k is approaching infinity of absolute value of a sub k plus 1. Well, in absolute value, these terms are just going to be transformed into 1, so I'm not going to write them anymore. So it's k plus 1 to k plus 1. I'm going to write it k plus 1 to the k times k plus 1 to simplify my computations as well. K plus 1 factorial, it's k factorial times k plus 1. And then times, and I'm going to put the reciprocal of a sub k, which is k factorial over k to the k. So this cancels with this one, and this cancels again, so limit as k is approaching infinity. And k plus 1 to the k over k to the k, we treat it a little bit different than if it was just k plus 1 to the second, for example. So I'm going to put k plus 1 over k, everything to the k in absolute value, which was an example that we did before. It was 1 plus 1 over k to the k, and this is equal to e. So this is e, which is greater than 1, so the series again diverges. Most of our problems diverge. Let's take a look at the root test. So the root test, here it's a typo. This should be a root test. So the root test says, let sum as a sub k be an infinite series. So again, the difference between this video and the previous video is here. In the previous video, we had positive series. And let rho equals limit as k is approaching infinity of k root of absolute value of a sub k. So the difference between these would be, here we have positive series and then we would have no absolute value. But this is more general because we calculate for any type of series. And of course, we are going to get that if it converges, it's going to converge absolutely, which is going to mean that it converges. And then if rho is greater than 1, that diverges, and rho equals 1, test inconclusive. And we have here a problem which we probably went over before. So I'm going to actually do a few problems that we haven't done before. So let's check if this series converges or diverges. So this quantity is this whole thing is our a sub k. So using the root test, and you might wonder why root test? Well, because it tells me everything to the k. So a ratio test would make it more complicated, maybe impossible to calculate. So rho equals limit as k is approaching infinity of k root of 4k to the third plus 7 over 9k to the second minus 1 to the k in absolute value. Let's not forget that to just make sure we have positive terms. Now this k from here cancels with this k, so we end up with limit as k is approaching infinity of 4k to the third plus 7 over 9k squared minus 1, which is infinity. So this means the series diverges. And I told you I want you to write in the test diverges by root test. Just specify which test you used. Let's try another one. Let's say sum as k goes from 1 to infinity of 1 plus 3 over k to the k squared, and I want to check using root test again. So rho equals limit as k is approaching infinity of k root of absolute value of 1 plus 3 over k to k squared. So now k with the square cancel and we end up with limit as k is approaching infinity of 1 plus 3 over k to the k. So this one is going to be equal to e to the third, because remember limit as k is approaching infinity of 1 plus a over k to the k, it's actually equal to e to the a. And if you are wondering why is that happening, well, it's because this term can be written e to k ln of 1 plus a over k, and so this term is going to be written ln of 1 plus a over k to 1 over k, which is going to give us the operation of 0 over 0 as k is approaching infinity. So we will have to use L'Hopital. So if you use that, you are going to end up with this term with the exponent equal to a. So the fact that we got e to the third, which is greater than 1, the series diverges by root test.